Be on time. Okay, so guys, good evening, everybody. Today, Dmitrii Rudenko will made a talk on Kaggle competition, IceCube, Neutrinos in deep ice. Thank you very much, Dmitrii, that you agreed to make this talk, and please start.
Hi, so I'm going to discuss with you IceCube Neutrinos in deep ice competition. I made a quick review to let you know something about this competition and like featured main models, main solutions for this problem, and even the problem and evaluation metric and so on. So yeah, what about me? I'm in Munich, Bavaria. Recently got Kaggle competitions expert level. So follow me everywhere. Presentation will be available a little bit later or right now. I don't really know. No, I cannot send it right now. So yeah, follow me. So the first thing is, what are we trying to do? We are going to predict the trace of neutrinos. Neutrinos are massless elementary particles, so we are going to use it to predict their track. Neutrinos are fundamental particles, so finding an accurate way to predict their track is very beneficial for science. The problem is that neutrinos are massless. As far as it's massless, they have so little amount of energy that they do not interact with anything except electrons. When they interact with electrons, they create Chervonenko flight, but we will talk about it later. So usually neutrinos are, the source of neutrinos are neutron stars, and finding out several neutrinos would help us to figure out where the space event happened, such as star collapse or black hole burning. As far as we're not into such a complicated thing, and neutrino idea is pretty fresh. I don't have any really accurate detectors as for light, for example. But we still have a theoretical way to find out neutrinos, and we have already detected several neutrinos. Existing solutions are pretty pricey, and that's the Kaggle competition where we try to create machine learning model which would help us to work with data faster and cheaper without using modern physics-based models, which are very reliable, but very slow, really slow. So what's the IceCube Neutrino Observatory? As you could see at the first slide, that's a polar station with such kind of detector. Let me draw. Oops. Yeah. So when we talk about observatory, we have it in such way. We have 1 square kilometer of isolation, which is ice. That helps us to avoid all other particles, such as photons, such as some electrons and space radiation, main part of space radiation. And we have detector part. Detector part is usually used to find neutrinos. So we have 1 square kilometer of ice isolation and then detectors. This is not lines, this is rows of detectors. So they have like the forest, detector forest. Let's go back further. How can I get rid of it? Then so the observatory is located on the North Pole, and as competition organizers say, the winner is invited to visit it. Okay. That's not a part of a prize, that's just an addition from the organizers. It's just 19 degrees from the North Pole, so that's a really redundant place. Let's go on. So yeah, that's a speed up physics Kaggle competition. You still need to improve slow and expensive method with your fast and very cheap model. And it means that there are several hacks to do it, like reading about physics, reading about the evidence, and usually easy and causal methods work better. It's this kind of competitions. Competition ends at 20th of April. The merge and join deadline at 13th. So you have some time to join it. But you have already lost a part of prizes. It doesn't matter how much prizes do they give for first, second, and third place. You can look at, you can see it in the slides. But they have 2 extra prizes sections. Early sharing prize already closed. It was till the 2nd of February, so you could easily get $1,000. That's crazy. Like if I could know about it, I would try to get, because it was really easy to get. You will see it in the models available, because every participant of this early sharing prize was into sharing their solution for everyone. So that's kind of warm up for Kaggle competition, pretty new thing. I'm happy to see such a practice at Kaggle. And they have best write-up. It's all about the final solutions. Top 30 participants at the private leaderboard at the end of the competition would get extra 1,000 if they have already got something. Scored by their write-up, such as code, reproducibility, innovation, and so on. That's great practice to as far as I see, because sometimes solutions are not reproducible at all. So data is pretty short in terms of features, but there are a lot of different events, and events are connected with each other. This observatory detects nearly 3,000 events per second. So the challenge is to improve localization, to limit observability, and the search space of a search space. They have 1 million events available during scoring during the test phase. So what about metrics? Metric is mean angular error. And that's not a common Kaggle competition metric, but very computationally useful. So the idea is to get azimuths and predict zenith pretty accurately. Azimuth is a vertical angle of the vector, and zenith is a horizontal angle of the vector. Authors score it as it's seen at the bottom line, but the short form of the metric is at the upper line. Why do the authors of the competition use such a prolonged formula? The reason is it's more computationally stable as far as we have very short range of azimuths. Main part of the neutrinos comes nearly perpendicular to the detector. So it's not from 0 to P, but main part of the distribution lies somewhere inside of this range. Okay. So yeah, you have pretty small amount of data: time, sensor ID, event ID, auxiliary, which is the quality of signal. I will tell about it a little bit later. And sensor location, because sensors are somehow located in 3D space. There are deep core and like upper core. And there is a hint. Deep core is more precisely calibrated. Deep core is more precisely calibrated. So you can see that auxiliary would affect it more. So auxiliary is the noise to signal ratio. And when you see auxiliary true, it means that we are not sure if it's a real signal or not. It could be just noise, just some kind of noise. But if auxiliary is false, you can see that the signal is pretty precise. Yeah, that's the detector model, and the line is the track of actual neutrino. Current solutions. So you can see that the best solution is GraphNet. It takes kind of one of mean auxiliary, one of the main metric. Then LSTM comes as far as neutrinos take time to like achieve the next detector. Dynamic edge, which got the prize for early solution, and just linear regression fitting with least squares, which took this third place for the early prizes. And the reference line is just Polar's empiric, which is very fast, lightning fast library written in Rust. Please use it. It's even better than pandas for computationally hard things because it utilizes all the cores of your computer. Also, other things. There is awesome scientific highlights for this competition. You can read a lot. You can get into neutrino detection and neutrino detectors. That's interesting for your development, even if you are into physics. And that's TUM affiliated competition. So I'm from Munich right now. TUM is a great research university. Follow it. And if you get some model which scores medal, you could get pretty nice chances to get funding or stipend in TUM. And also follow me. I'm having a Telegram channel, writing sometimes about Kaggle and different solutions. That's it. Thank you.
Okay, thank you very much, Dmitrii. So, colleagues, please, any questions or comments or suggestions or whatever? Let me. So now you can unmute yourself and ask a question by voice or write it in the chat. It's up to you. So maybe let me ask the first question. So what about the data? It's kind of a table data composition, or it's, what is?
Yeah, let's get back. So you have a parquet file for everything except sensor location. Sensor location is stored in CSV, but it's kind of object detection in space competition. So as far as you can see, there are several graph-based models which achieve the best performance. And that's what you need to do here, like predict the track of the neutrino using such kind of model, or just linear regression, fit it as you want. That would work too. The great thing here is they don't have any like standard metric for evaluation, so you could find some kind of hack to achieve better score.
Thank you.
Like let's look again at the example. That's one object of this competition. We need to predict this line by
just a moment. So I see that there are many vertical lines which I understand as a kind of detectors. Yes.
Yeah.
Right?
Every dot
Gray.
of this line
yes,
is
and
detector.
so there are these kind of colored spots. They correspond to event. Yes. Or
yes, colored points are detector interaction with neutrino. More than that, theoretically, it can have like two kind of interaction. If neutrino moves really fast, it could produce some Cherenkov effect, which would create a resonance cascade, as you could see. Like you could see one cascade in Half-Life 2. Cascade resonance, but yeah, mainly at this competition, you have just auxiliary false events.
So these spots, they're given by kind of position of the detector. So they're just the set of the three-dimensional coordinates. Or
I see. So you are given the detector's interaction itself, and you need to predict the line. So every point here is just detector's interaction at the time. As far as you have two-layer detector with deep core and like upper core, you have to augment your data. You can augment your data by rotating it by z coordinate. So just rolling it horizontally around the horizontal axis.
But still, in the sense of the just numbers, each event is how many numbers? So it depends on event, or
yeah, it depends on the event. Every event can have from just one detector interaction up to several hundred.
okay, so we have these events, and we should find this the angular, the direction of this red line.
Yes.
Yes, is correct.
Zenith and how did I said it? And azimuth.
Okay.
You're not really asked to find out where exactly this event happens, but you need to find out if this event has any, which angle it has. It's needed to estimate where it comes from and where the space event happens, such as neutron star collapse or black hole burn.
Okay. So in some sense, it's like a tabular data competition, but it's not a tabular because we, for each event, we have different number of features, and the features are not kind of. Okay.
I would say that's graph regression computation.
Where is the graph? I don't understand.
As far as you have several hundred detectors, and theoretically every detector can be interacted separately, as you can see at this picture, for example, you have different number of features, but you can still try watching, like looking at every detector as a feature, but it wouldn't be very effective. I forgot to say, every detector has like probabilistic charge. So it can have charge of 2.7, which would say that, okay, there were from 2 to 3 electrons interacted with neutrino, but we don't really know 2 or 3. We know that, okay, that's closer to 3. Theoretically, it can be like 5, but we have detected only 2 and 2.7.
It corresponds to something like color on the previous.
Color and size. You can see that various.
Okay.
Yeah, color. You can see that this one is bigger than this one, for example.
Okay. Still, what kind of graph? It's a graph for each event, or it's a one graph for all events?
Graph for each event, and that's the interest, because it's hard to use this thing. That's why the main solutions the best, the most precise solutions use graph-based models like dynamic edge model and GraphNet. Usually these models are used for classification of objects in 3D space, such as point cloud detection, point cloud classification, such things.
Oh, okay. But I'm not sure I understand how they construct a graph from this event.
Imagine voxels and imagine, the glass transferred into the voxel representation. So you use just 3D convolutions to figure out, is it a glass or just, a cup or even pretzel. Okay, imagine we have image. That's 2D space representation of object. That's projection of 3D space. And then imagine that we use the same technique to create the 3D representation of the object. We just create voxels instead of pixels. And that's how graph neural networks work. They are working pretty the same with convolutional networks, but in 3D space.
So each event is encoded as a graph. There are some features probably.
In these terms, each event can be encoded as a graph, but not exactly. You can still use linear regression just to find out where detector located and create the line using just least squares method.
Yes. So how the graph appears?
By the interactions with detectors. Like not every detector registers the neutrino. So they don't provide you interaction from these exact graphs which were not affected by neutrino. As you can see at the picture, where we see the colored points, there were some interaction from with electron and neutrino, but inside but everywhere else where you see the gray dots, there is nothing. No interaction, and we don't see this we don't even see these points. We can reconstruct it because we know every detector's location, but it doesn't matter. They just don't register anything.
Okay, thank you. So colleagues, any other questions, suggestions, comments?
Yeah, even Russian.
Oh, yes, yeah, in Russian. Maybe one more question. So what are people now doing? Some, I don't know, staking, blending, usual Kaggle stuff or not? It's not more like domain knowledge. So what is more domain knowledge or
right now that's an
Kaggle?
early stage of competition. So you have, 2 months extra, or even more than 2 months. So You can join and flex at the leaderboard at the top. The main part of competitors will appear later. What is important here is that sometimes people give you early sharing price, and this time no one really participated in the competition. Like least squares algorithms and polar least squares empiric got $1,000. So just monitor every new competition to find out if they have such kind of prizes. That's easy money.
Okay. And about the data, as far as I've seen, there was about more than 100 gigabytes of the data. Yes.
Yeah, they have a lot of data. That's why they put it into Parquet format.
How to deal with that on Kaggle? As far as I understand, we have only 30 gigabytes of RAM.
Batch-wise, like you don't really need to load everything. You still can use it batch-wise. For example, for least squares, they just used the next thing. They loaded one sample, created least squares approximation of track. They write the answer, and then they go to the next event. So one by one, these events are easily used to, easily handled. And that's how you can do it in neural networks. You don't even need to load the whole data set into the memory.
Do you have an idea how much these substitutions, how much time they work? So on Kaggle, we have something like 12-hour time limit. So
yeah, so that's not. I don't think that it's really a complicated task. As far as you are dealing with really finite number of observations, which is even less than average computer vision competition, where you have kind of 3 channels for 1000 x 1000 points. Here you have kind of, I don't know, several hundreds. So main solutions, even the hardest one, run into like 2 hours.
okay,
like this competition looks really interesting. I might join it, but a little bit later because I'm participating into breast cancer right now. I will try my best at the breast cancer and then stick to the IceCube. It looks fancy. That's non-standard task, so can be useful.
Okay, thank you very much. Any other comments, suggestions, questions?
I wanted to ask something about the data. Yeah, so do you make a graph structure on your own, like like this voxels, yes, and then pass it to the model, or how do people usually organize it? So is it in any case profitable to maybe to play with the structure of the graph and maybe, I don't know, look at some few other cases?
That's a nice question. Like, yes, the structure of the graph could be really important in terms of using auxiliary true samples. As far as I've seen, current solutions doesn't use it at all. But that's pretty physics-based computation. So you're still having a graph in 3D space. And that's why you cannot stick to something really graph-based. You still have to utilize 3D space. It wouldn't be like just stupid not to use it. But for every detector, you have different level of calibration. That's just physics problem. Somehow it occurs. So every graph is correlated, every detector is correlated with other detectors, and your model should understand which detector is overconfident, which is underconfident, and so on.
Okay, and about the model, so is it just a bunch of graph convolutions or maybe something more difficult?
I would say that dynamic itch is just a bunch of graph convolutions. LSTM doesn't use convolutions at all. They're using just embeddings of every detector. And GraphNet utilizes some kind of graph structure, but highly dependent on like close. That's something kind of something between just 3D space convolutions and graph convolutions. So GraphNet achieves the best score. So I would think about it. But I really believe that linear regression, fancily tuned, can get a pretty nice score here.
Great. So is it possible maybe to run it off your laptop or maybe it's some cloud things or?
Yeah, for sure you can run it at Kaggle. I'm looking at the main public, like the best public solutions. So that's just it can be run at the Kaggle. As far as it can be run in the Kaggle, you can run it at laptop. You can run it at Google Cloud. Every object is very small in comparison with images, for example. So for sure you can run it at your laptop. It only depends on the speed of your processor and disk and so on. But there is no borderline for memory.
Okay, thank you.
Thank you. Any other questions, suggestions, or comments? Okay, so if no,
are you planning some continuation of this topic further?
Yeah, if I would like to participate in future at this competition, I would write a follow-up for it, for sure. So yeah, follow the Berloga channel and even my channel. I will write updates there.
Okay, thanks.
okay. Any other questions, suggestions, comments? Okay, so if not, then thank you very much, Dmitrii, for very interesting talk. So we'll put it to YouTube soon. And good evening, everybody. So let me close the meeting.